Bismillah ar-Rahman ar-Rahim. This is lecture 4 on Cramer's rule and inverses. Okay, Cramer's rule is a rule for solving ax equal to b. You remember that in solving ax equal to b, x equals a inverse b, a inverse has the determinant dividing every term. So every component of x equals a inverse b will also be divided by the determinant of a. To develop Cramer's rule, let us start with a 2 by 2 matrix. So ax equal to b is the matrix a11, a12, a21, a22 times x1, x2 equal to b1, b2. Since a inverse is 1 over determinant of a times a22 minus a12 minus a21, a11, as we have seen before, then x1, x2 is 1 over determinant of a when multiplied by b1, b2, we have the first element, which is x1, has b1, a22 minus b2, a12, and second element, x2, will have minus b1, a21 plus b2, a11. Note that these can be written using determinants as follows. x1 is 1 over determinant of a times the determinant with b1, b2 in the first column, a12, a22 in the second column. So we can write x1 equal to determinant b1 divided by determinant of a, and x2 is the determinant a11, a21 in the first column, b1, b2 in the second column, divided by determinant of a, so it is determinant b2 over determinant of a. We see here that the first column of b1 is really ax equal to b. The second column is a times the second column of the identity matrix, because if you take a times the identity matrix, you get a. So the second column here in b1 is really a times the second column of the identity matrix. So if we combine these two together, okay, b1 is really a times x1, x2, and 0, 1. Okay. Similarly, b2 is a times the first column of the identity matrix and x1, x2 in the second column. Let us do it for a 3 by 3 matrix. Ax equal to b here has b1, a, which is a1 as a vector, a2 as a column vector, a3 as a column vector, times the identity matrix with the first column replaced by x, x1, x2, x3, and this will be equal to the first column in B, and the second is a2, the third is a3. Okay. So this is b1. And b2 will be the same. We replace the second column of the identity matrix by x1, x2, x3, and this will be a1 in the first column, b and a3. Okay. So b3 again will be replacing the third column of the identity matrix with the x, and we get the matrix A with B in the third column. Taking determinants, we will find that x1 times determinant of A is equal to determinant B1, x2 times determinant of A equals determinant B2, x3 determinant of A equals B3, or xi in general is determinant Bi over determinant of A. This is Cramer's rule for the solution of x equal to B. Now, we would like to find a formula for A inverse using Cramer's rule. We do this by letting the right-hand side B be one of the columns of the identity matrix. Okay? Because A times A inverse equals I. Okay. So we do this using an example with the matrix A 1, 1, 1, minus 2, 1, 0, minus 4, 0, 1 times x1, x2, x3 equal to the first column of the identity matrix. Then to apply Cramer's rule, we need to calculate determinant of A, which is determinant of U, which we can use by Gaussian elimination. We find the product of the pivots, 1, 3 times 7 over 3 is equal to 7. Then determinant of B1 equals 1. Determinant of B2 is equal to 2. Okay. And determinant of B3 is equal to 4. Well, about the sign change in B2, see, when we expand by the column here in B1, the subdeterminant or the cofactor of 1 is this matrix 1, 0, 0, 1. So we take the determinant of that, it is equal to 1. And the order of the columns here follows the sequence 1, 2, 3. Okay, so the cofactor has columns 2 and 3, and this sign is positive. If we go to the second B2, in B2 we expand by the second column. Now the submatrix, okay, subdeterminant, which is the cofactor of the 2, 1, of the 1, 2 element here, the first row, it has to go the order 3, 1 to be positive, but here it is 1, 3. If you go 1 to 3, you go against the arrow, so it is negative, so we have a minus sign. Okay, so actually it is minus 1 times the first column, then the second column, okay, which comes to plus 2. For B3, the determinant is again expanded by the third column. We have only one term, and the cofactor is 1, 2. So 1, 2 positive. Okay, so it is 4. If we divide by the determinant of A, which is 7, we get x1, x2, x3. This is the first column of A inverse. To get the second column of A inverse, okay, we let the right-hand side be the second column of the identity, which is 0, 1, 0. Okay. Now, there's an important point here. Watch for. When B is 1, 0, 0, and if you put that in the first column of A to produce one of the B's, the determinant is just 1 times a cofactor. Okay, the numbers 1 to 4 are really cofactors in the matrix A. Okay, and a cofactor has smaller size, that is 3 minus 1 is 2. And we look back to see how each B is a cofactor. Okay, the cofactors have signs plus, minus, plus. So we are expanding by the first row of A. Okay, so the determinant of B1 is 1. It is the cofactor C11 of A, which has a plus sign, and it is just 1, 0, 0, 1. The determinant is 1. And B2 is the cofactor C12, which has a minus sign. Okay, so it is 2. And B3 is the cofactor C13, which is positive, it has a positive sign, plus 4. And these cofactors are the cofactors of the first row of A, but in A inverse they go in the first column of A inverse. Okay, so they are transposed. The cofactors are transposed in A inverse. Now for the second column of A inverse, as we said, we change B to 0, 1, 0. Now watch how the determinant of B1, B2, B3, okay, these are cofactors along row 2 of A, including the signs minus, plus, minus. So this is B1 and B2 and B3, which are obtained by inserting B, which is 0, 1, 0, in the first column for B1, and in the second column in B2, and in the third column in B3. And the signs, as I said, are minus, plus, minus, minus, plus, minus. Divide this by determinant of A, you get the second column of A inverse. Here the cofactors for the second row were C21, C22, and C23. Okay, and they go into the second column of A inverse. So again, the row is transposed into a column in A inverse. Row of A goes into a column of A inverse. Okay. For the third column of A inverse, the right side is B001. Okay, which is the third column of the identity matrix. Now the three determinants of the B's become cofactors along the third row of A, and here the signs are plus, minus, plus. Okay, so we evaluate those from the B's, where here we have inserted 001 in the first column for B1, in the second column for B2, and in the third column for B3. Okay, now we have the matrix A inverse. So A inverse, A times A inverse equals I. Note that the cofactors were obtained by using the rows of A. Row 1 gave the cofactors that went into column 1 of A inverse. Row 2 gave the cofactors in column 2 of A inverse. And row 3 gave the cofactors in column 3. Putting these into A inverse equals I, we have A times C transpose. A times C transpose equal to I. Since A inverse has the determinant of A dividing every term, so A times CT is determinant of A times I. Or A inverse is CT over determinant of A. Okay. The ij term of A inverse is Ji over A. The transpose ij becomes Ji. This is the quickest way to calculate A inverse by using cofactors. Now, let us move to applications of determinants, and the application here is calculation of the area of a triangle. Of course, we know how to calculate the area of a triangle, which is 1/2 the base times the height. Okay, but if we only know the corners of the triangle as x1, y1, x2, y2, x3, y3, how do we calculate the area? To start, let us assume that x3, y3 equals 0, 0. Then we can use vectors and lengths to compute the area as follows. Let A be equal to the vector x1, y1, which is the vector from 0, 0 to x1, y1, and B, the vector x2, y2. The perpendicular to A taken as a base of the triangle, is the error vector. The error vector is E, which is B minus the projection P onto A. Okay, B minus A transpose B or A transpose A times A, which we calculate as follows. After simplification, we find that E is this 1 over norm squared of A, which is x1 squared plus y1 squared, times y1 times x2 y1 minus x1 y2, the first term. The second term is x1 times x1 y2 minus x2 y1, which is the same as above but with a minus sign. Now, if we calculate the area, we need the norm of A, which is square root x1 squared plus y1 squared, and norm of E, according to the formula, is square root of x1 squared into x1 y2 minus x2 y1 whole square plus y1 squared times the same thing divided by x1 squared plus y1 squared whole square. So the square here cancels with the numerator, and we take the square root and we get norm E. Okay, this is norm E. Now the area is 1/2 norm E times norm A, which is 1/2 x1 y2 minus x2 y1. Okay, and this can be written in the form of a determinant, 1/2 the determinant x1, x2, y1, y2, when x3, y3 equals 0. Now, if x3, y3 is not the origin, it's not 0, 0, we can use the above formula by adding the areas of 3 triangles as shown. So we have 3 triangles. This would be the area for the triangle between x1, y1, x2, y2. So we can easily extend this to find the area here between x2, y2, x3, y3. It is 1/2 x2, y3 minus x3, y2. And the last one will be 1/2 x3, y1 minus x1, y3. We're just following the order 1, 2, 3. Okay. Okay. Now this can be written in terms of determinants as before. This is the first one. Second one, 1/2 x2, x3, y2, y3. And the last one is x3, x1, y3, y1. So the rows are exchanged here. If we exchange the rows to put it in the same order, x1, x3, y1, y3, we have a minus sign from the rules for determinants. Okay. So if we put this here, then these can be written as one determinant, which if we expand, okay, we have x1, x2, x3 in one column, y1, y2, y3, and then 1, 1, 1. If we expand by the third column, we get these 3 terms. Okay, so this is the rule for finding the area of a triangle if you know the vertices. Okay, and this formula is very useful in applications. In surveying, for example, when surveyors calculate areas, they take 3 points and they calculate the area, and this is called triangulation. They calculate the areas by triangulation. Okay. So this ends the chapter on determinants. The next chapter will be on eigenvalues and eigenvectors.